begin the last talk of this section. And it's a pleasure to introduce Miriam Telichevesky from Federal University of Rio Grande do Sul. And she's going to talk on regularity at infinity of Hadamard manifolds with respect to some elliptic operators with application to asymptotic Dirichlet problems.
Thank you. It's okay. Thank you very much for the time to make the invitation to come and give this talk. It's a pleasure to be here. And I will talk about part of my PhD thesis. It has this big title, Regularity at Infinity of Hadamard manifolds with respect to some elliptic operators with applications to asymptotic Dirichlet problems. And it's a joint work with Jaime Ripoll, my advisor. So, the setting is the following. M is a complete simply connected Hadamard manifold, which is a Hadamard manifold because it has sectional curvature bounded from above by -1. In fact, we can think about minus k to the square, where k is a constant, a positive constant, but it's the same of thinking about -1, and I will think about -1 every time because it's a little simpler. I will denote by partial with infinity of M, the asymptotic boundary of M, which is the set of classes of equivalences of closer geodesics. And we can think about M as being a ball because it is diffeomorphic to the Euclidean space, and it's diffeomorphic also to a ball. And the asymptotic boundary may be identified with the boundary of the ball, and if we take this picture in mind to continue. And I will denote by M bar this union, the M with its asymptotic boundary. It's the compactification of M with respect to the cone topology. A neighborhood of a point at infinity is a truncated cone. We think about a cone that has its point at infinity and truncated at some finite distance, and it's a neighborhood of a point at infinity. And with all these truncate cones, we consider all the balls, and we have the cone topology. It's what is the cone topology. And the problem I am interested in is the asymptotic Dirichlet problem. Since it's a topological thing, I can think about continuous functions defined in there, and I'm looking for a function that satisfies. Its graph is minimal, and its restriction to the asymptotic boundary is some data prescribed, continuous data prescribed. A remark, in fact, the results we obtained about the mean curvature operator can be extended to a bigger class of operators, which are given by this expression, where A is a C1 function with some properties. I will leave it in the blackboard for some. The first condition, all the conditions are technical conditions for things going right. But what we see is that they imply for some q greater than 0 that the P-Laplacians are also included in the class of operators that we are considering. And of course, the Laplacian, the usual Laplacian is also considered. Oh, sorry, I forgot something here. Okay, now it makes sense. And the asymptotic Dirichlet problems for Laplacian has been investigated at least for 3 decades. And for P-Laplacian, on the last decade, as I saw. So we are, our main interest is in the minimal equation and the mean curvature operator. But with our techniques, we also obtain results about the other operators. So I will talk about basically on the minimal, but you can think always about the general operator. Okay, so how we find the solutions of the asymptotic Dirichlet problem, which I will call ADP. The first step is to find a global solution of the PDE on M. And it is possible only with only the hypothesis on the curvature, and we don't need anything else. Of course, Hadamard manifold, and we feel happy. Okay, but the second step is to guarantee that the solution stands continually to the asymptotic boundary and assumes the prescribed data. And what we see is that only the assumption that K, the curvature, the sectional curvature is bounded from above is not enough, because we have counterexamples. From Ancona and Borbelli for the case of Q equals to the Laplacian. From Ilka-Holopainen for the case of P Laplacian. And what we thought is that probably it would be some counterexamples for the minimal case also, and Ilka-Holopainen and Jamie Paul got these counterexamples for mean curvature operator. So just the hypothesis of K sectional curvature bounded from above is not enough to have the solution of asymptotic Dirichlet problems. And we don't know what to do. So the question is, what do we need to guarantee that the prescribed boundary data is assumed, in fact? And we got the inspiration from what was done about the Laplacian. We need the regularity of the asymptotic boundary. The existence of lower and upper barriers at each point of the asymptotic boundary. Recalling what is a barrier at infinity is if you have some point here and the neighborhood of it, which I call omega, a barrier is just a super solution. An upper barrier is a super solution. I don't know how to draw it. It's horrible, don't look at it. Just keep in mind. It's a super solution that when we are on the compact case, we need that the super solution is 0 at this point, but it does not make sense on on a point that is at infinity, and then we require this thing, this limit. And also we need that it's non-trivial. It has some fixed it is bigger than some constant outside of the neighborhood of x that's given by this condition. And we need it to compare with the solutions and conclude that the solution is below than the upper barrier and above the lower barrier. Just a remark, this definition is a little bit different on the case of delta, of the Laplacian, because we don't need this C to be arbitrary. We need just one, for instance, because the Laplacian is linear, and we may multiply by any constant, and we can obtain any constant we want. But since we are working with operators that are not linear, we need to require that this C must appear on our definition. We need a barrier relative to x, to a neighborhood of x, and to a height C. And we say that M is regular at infinity if it admits barriers for every x, for every neighborhood of x, and for every height C. And with these assumptions of regularity, and also with the assumption of Km less or equal to -1, it's possible to prove that the asymptotic boundary data is assumed by the global solution that we have already obtained, and we feel happy again. But the question is, what geometric conditions on M imply the regularity at infinity? Okay, again, we find inspiration, or we look for inspiration on the case of the Laplacian. To prove the regularity at infinity with respect to Laplacian, Choi defined in 1984 the convex conic neighborhood condition, which is the following. Given two distinct points of the asymptotic boundary, there exists C2 open disjoint convex conic neighborhoods of them. Yeah, that's it. There exists two disjoint C2 convex conic neighborhoods of them. And with this condition, it is easy to prove that the manifold is regular with respect to Laplacian, because we consider you need to construct barriers at some point. We consider a point and a neighborhood, omega. And for each point at the asymptotic boundary of omega, there exists some neighborhood which does not intersect another neighborhood of x. And you have an opening cover of the boundary of, this is the asymptotic boundary of omega. You extract a subcovering that is finite, and you sum. The main point is the following. My pictures are terrible, sorry. You have some neighborhood here. Let's think about the two-dimensional case. It is easier. X1, X2. These two are the asymptotic boundary, and you have this. This is convex, sorry, with this orientation. And what we do is what we do, what Choi did, is to consider the distance function to each of these neighborhoods, to each of the boundary of its neighborhoods. And the distance function, and here the distance to partial omega 2, they satisfy, let's say S1 and S2, they satisfy Laplacian of S is bigger than n minus 1 hyperbolic tangent of S, and the other the same thing. And with these estimatives that follows from comparison theorems, it's easy to get a barrier at infinity because we can sum things, you can add things, and when you add these things, you obtain a barrier. But we can't do it on the case of minimal surfaces, of minimal graphs, because we don't have linearity, and it's impossible to do exactly what Choi did. And we tried to adapt something, and it wasn't easy because what we need to construct a barrier is to go on the direction of X. And here we are going some kind of the opposite direction that we want to go. So what we did, we tried to do another definition of convexity that was good for us. And we call it the strict convexity condition at infinity. What this condition said, we said that M satisfied the strict convexity condition at infinity, and we abbreviate by SC condition. If given any X of the asymptotic boundary, and given any W neighborhood on the asymptotic boundary, there exists a C2 open set omega, such that the asymptotic boundary of omega is contained on W, and X belongs to the asymptotic boundary of omega. And the main part of the definition is that this set, that is M minus omega, is convex. And what we get with it, the distance function, if we consider the distance function to the boundary, the distance function to the boundary, S going from omega to R, we get the Laplacian of distance is bigger than n minus 1 hyperbolic tangent of S. And that's what we need to construct the barriers. A remark, after our work was done and anything else, we found out a definition given by Peter Lee that's equivalent to ours. It is named the separation property at infinity, and he used this definition to study some properties of harmonic maps on Cartan Hadamard manifolds. We didn't try to relate the studies done by Peter Lee with our studies because we recently discovered this definition, and we didn't have a time yet to do it. But we felt happy because the definition we gave is not so strange. Someone has already think about that. And the main result is that if M is a Hadamard manifold with sectional curvature bounded from above by -1, that satisfies the SC condition, then M is regular at infinity with respect to these operators. And the proof is really simple. It's just consider the adequate function. I will do it fast because it's not very important. It's just define the distance function and the adequate function to be a barrier. That is this one. C. C is a constant to be chosen. G of x is this, yes. And it is a solution in the case that the manifold is the hyperbolic space, and the boundary of omega is a totally geodesic hypersurface because it's when holds equality here. And we get that, not this function, but the composition. Define V of x as being G, V of x as being G of S of x. And it is a solution in this case. Okay, I will go faster. And the question, so, what geometric conditions imply the SC condition? We always go and make another new question to get something because we don't want to prove a theorem about the empty set. And nobody wants. The first geometric condition is the dimension 2. It's easy because the condition on the curvature implies that given any 2 points at the asymptotic boundary, there exists a geodesic joining them, and then the geodesic separates the manifold on 2 convex sets and follows the condition. It's just choose adequate points. And here we extend the results from Choi about Laplacian. He already made this remark on his work. And from Galvez and Rosenberg about the mean curvature operator, they also proved the result about existence of solution of the asymptotic Dirichlet problems with respect to the mean curvature operator on dimension 2. Another case is the controller decay on the sectional curvature. If it does not, if it does not go too fast to minus infinity, it can be proven also that it satisfies the SC condition. And for this, we follow a construction made first by Anderson to prove choice condition on the case that the curvature is bounded from above and below by constants. And after from Borbelli, that used a similar condition that this, but he has a constant 1/3 here that I don't know why. He has a constant, but it's the same construction. And we can do the same construction to find that our condition is also satisfied with this hypothesis. And when we do this, we extend the results from Borbelli about the Laplacian and from Ilka Holopainen and Alexei Vahakangas for the P Laplacian. But the case of mean curvature operator is new on this example. And finally, the rotationally symmetric manifolds. It's very funny. what we do is the following. A rotational symmetric manifold has the metric given by this expression, where r is the distance function to some pole, and d theta 2 is the metric on the sphere. And what happens is the following. Hn has the function hyperbolic sine of r to be this function. And we know that there exists a totally geodesic hypersurface in Hn. It's easy to get. What we do is the following. We express in terms of, we do it by hand. We say the equation of this set. If we can think about the ball model, we can think about Rn with this metric, because it's when the thing works. And we say, this set is given by the following expressions. I forgot to mention there, but we have expression that says what r and theta there must satisfy, theta 1, theta n minus 1, must satisfy to belong to this set, totally geodesic. On Hn. And then what we do is to keep the same set and change the metric to this one and make some computations and get the convexity for the right side. It's very interesting way to do. And this extends the result was already known for rotationally symmetric manifolds about the mean curvature operator. And some open questions to finish. What do our convexity condition, choice convexity condition have in common? We didn't discover yet. Can we adapt some techniques to obtain results about minimal or CMC killing graphs instead of minimal graphs on n times r? Is it possible to let the sectional curvature goes to 0 with another extra hypothesis and obtain again solvability of asymptotic Dirichlet problems? It's very studied about the Laplacian, and we want to get results about minimal equation or another P Laplacian equations and many other questions. Thank you for